and 4 minus root 6. What's weird? The 2i and 4 minus root 6. I mean, you don't really know what those are, do you? 2i is 2 square roots of negative 1. That's what it is. 4 minus root 6, all I can tell you is it's negative. Actually, can I even tell you that? No, it's not. It's actually positive. That's about all I can tell you. It's a little over 1 maybe. But those are weird. So since 2i and 4 minus, I don't have the square root key here, square root of 6 are weird, they have conjugates. What are they? What's the conjugate of 2i? Conjugate of 2i is negative 2i. You did that in IXL. I don't know if you remember that or not. What's the conjugate of 4 minus a squirt of 6? It's quicker for me to type square root squirt than it is to draw in a square root symbol. What's the conjugate of 4 take away a square root of 6? No. It's 4 plus square root of 6. So what a lot of kids do is they mess up signs. To form a conjugate, you just change the weird pieces sign. Just change the weird pieces of sign. I don't know. I don't know if that's a word. I don't feel like I spelled it right. Just change the weird things sign. Let's do that. There we go. Whatever's weird, change the sign. So we have all that. Now we actually know all our zeros. Our zeros are 2, 2i, negative 2i, 4 take away a root of 6, and 4 plus a root of 6. And let's write out the polynomial. I don't know if you remember yesterday or not, we did a lot of distributing and stuff like that. Remember that? I remember it. So we'll just call it f of x. First up is the leading coefficient, better known as a. What's the leading coefficient? 3. Here's the first zero I'm looking at, 2. The first zero I see is 2. What factor creates a zero of 2? X minus 2. When we enter parentheses, we change our signs. And factors contain x's. Really all there is to it. Alright, next zero I see is kind of weird. It's 2i. What's the factor that creates 2i as a zero? X minus 2i. Remember I told you yesterday that if Jesus Christ was down here, he too would tell you just to change the sign and don't overthink it. Then we did a conjugate. Parker, the zero is negative 2i. What's the factor? X plus. Don't forget the x. X plus 2i. All right. Then we got a weird zero. 4 take away root 6. Alex, the zero is 4 take away root 6. What's the factor? No. What is it, guys? Plus. Change signs. Minus 4, it was positive. Plus root 6, it was negative. Change signs. Don't overthink this. If there was 16 things going into this factor, how many times would you change signs? 16 times. That's all there is to it. And the last zero that we figured out was 4 plus root 6. What's the factor? No, not plus 4. Minus 4 minus root 6. And unlike yesterday, we're not going to do a lot of foiling. I just don't have time for it. But I wanted to go over the idea of changing signs when you have parentheses. That's really all there is to it. It's not a hard skill. I've been telling you since August, change signs. In a minute. All right, 1 of 8 done. Then we get to talk about 5/8. 5/8 is analyzing the graph of a polynomial. First concept is end behavior, which was taught in 5.2. I think it's 5.2. Is that a 5.2 or 5.3? This is an odd degree positive a, so like x to the third, x to the fifth. You remember how x cubed or x to the fifth start their day? low, ends high. That's what they do. If you have an odd exponent, you start low, you end high. What happens if that leading coefficient becomes negative? Starts high, ends low. By all means, use your hands to do it too. High to low. Moving down underneath, we start talking about even exponents, like x squared, x to the fourth, x to the sixth. Just focus on x squared. You've been graphing x squared for 2 months now. How's x squared start? Starts high, ends high. All even degrees do. What if the coefficient up front becomes negative? Low, low. So there's the recap from 5-2. And maybe, which is most of a graph. Almost all a graph is n behavior. All right. Next up in your notes is the definition of a power function. A power function is the term with the highest exponent, or the leading term when you write it out in standard form. That's what a power function is. It's a term with the highest power when written in standard form. Term is the majority of the graph's behavior. I also modified the problems just a little bit. I don't know where you're at yet. Now, the definition of power function talks about being written in standard form. How long would it take for us to take f of x and put it in standard form? I'd say best guess 5 minutes. That'd be my best guess if we do it as a class. It'd take us 5 minutes. I ain't got 5 minutes. Nice thing is, to find a power function, you don't even have to put something in standard form. You get to do near math. You don't have to do all the math. You get to do near math. What you do is you just think about what power, what x value you get from each factor. So that's what we're going to do. We're going to do near math. We're just going to think about the x we get from each factor. Then we're going to put them all together. All right. Now, I did modify that x squared minus 5. I gave it an exponent of 2. There's nothing on my wall, Nathan. I did give that x squared minus 5 an exponent of 2. Okay, I modified it a little bit. The power function's obviously going to inherit that 1/10 of things don't get. Right? That's got to be part of it. That's the leading coefficient. At least in factored form, it's the leading coefficient. So the power function will get that 1/10. What's it going to get from x minus 4? Just going to get an x. That's all it's going to get. If you were to actually completely FOIL out x squared minus 5 by writing it twice and FOILing, what would x squared minus 5 get you? What power of x? It gets you x to the 4th. We're doing near math here. We're not doing all of it. We don't have to get a power function. It's going to grant you an x to the 4th. And what kind of x would x plus 3 give you? Just gives you an x. There's lots of kids out there that think you can, properly get an answer by just distributing over and over and over. You can. That just gives you a power function. That's all it actually gives you. It doesn't give you the full story. But this gives you a power function. What's the power function end up being? It's a tenth times an x times an x and a fourth times an x. A tenth of x to the sixth. So we get 1/10 of x to the sixth because these had understood ones as exponents. And we multiply like terms, we add exponents. So now I actually know how this function behaves. This particular function, how would it start its day? High. How's it end its day? High. It's an even 3. I modified the second one, g of x, as well. I made that last factor 3x plus 3. The notes have x plus 3. So I made the last factor 3x plus 3. Now we're going to make the power function. I'm tired of writing power function, so I'm just going to write poof. What's something you get just off the bat? You get -1. First thing you see. What power of x do you get from the factor x minus 4? You just get 1 times an x. What do you get from 3x plus 3 squared? That's right, Bella said 9x squared. You talk about 3x plus 3 squared, you think in your head hopefully about writing it twice. And these have x's, and you link them together, you get 9x squared. So they're actually inheriting a 9 in addition. You guys get that? We're doing near math. We're not doing all the math. We're just doing a little bit just to get the power function. We end up with -9 x to what power? Third. How does -9x cubed start its day? Why did I look at the notes you did? Nope. Starts high and low. It's -9x cubed. Negative. That causes a reflection on the x-axis. Starts high and is low. All right, next up in your notes is the multiplicity of the zeros. You actually have fewer notes here than you took yesterday. Multiplicity was introduced yesterday. Got a graph. Spent a lot of time talking about that graph on the calculator. Multiplicity is found simply by looking at exponents. That's all you do. You look at exponents. All right. This factor x minus 4, what's its multiplicity? 1. Because the 1 is the understood exponent. All right. This factor 3x plus 3 squared, what's its multiplicity? 2. That's how you find multiplicity. It's a really easy thing to do, but some kids don't know what exponents are. You'd be amazed at how many kids don't know what an exponent is. It is ridiculously high. It's like 20–25% of the student body. You could write down 4 squared and ask them what the exponent was. They'd say 4. You just don't know. It blows my mind. But anyways, that's just a rant. Does everybody know what an even number is? I hope so. Do you remember what even multiplicity does on a graph? It touches, right? Even multiplicity touches the x-axis. And it is even. And the definition of even is we happen at least twice. Could be 2, could be 4, could be 6. It would definitely be even. Could be 2, 4, 6, ... But you happen at least twice. And it is a touch on the x-axis. That's probably the most important part of it. Odd multiplicity, what's it do as far as the x-axis is concerned? Runs right through it. Most math teachers call that a cross the x-axis. And they happen at least once because it's odd. It could be once, could be 3, could be 5, could be 7, so forth. Anything with odd multiplicity is going to cross the x-axis. Anything with even is going to touch it. And that's just basically a restatement of yesterday's notes on that part. Nothing new there. No graph this time. So your next example is where we roughly sketch something. That's all it is. Roughly sketch something. Roughly sketch y equals 1/6 of x plus 3 times x minus 2 all squared. I'm actually in Algebra 2, and I've been meaning to pull these from the notes. I'm not worried about step 3. If you were in pre-calculus, I would make you draw nice graphs by hand without a calculator, but you're not. You're just in Algebra 2. Your little ones, you don't know anything yet. So, step 3 is gone. You got a function in front of you. So y equals 1/6 of x plus 3 times x minus 2 all squared. Step 1 is to plot the zeros. If x plus 3 is a factor, what's the zero? X is -3. If x minus 2 all squared is a factor, what's the zero? You're overthinking. You want to say 4, don't you? X minus 2 is 0. What's x? 2. It's that square, boy, it throws kids off. I mean, it could just be written twice. And since we're finding zeros, we just set it equal to 0, right? You're overthinking about the exponent. All that matters is the actual factor itself. All right? Now, something that should be listed up here, and it's not, it talks about multiplicity. Multiplicity is just abbreviated with the letter M. Multiplicity needs to be talked about. The 0 at -3 has a multiplicity of what? 1. Why? Why 1? Understood exponents. Understood. There's a 1 there. The 0 at 2, what's its multiplicity? 2. Exponents at 2. What do you know about a multiplicity of 1? Crosses. That's a crossing. Odd multiplicities cross. Cross the x-axis. How about having a multiplicity of 2? Touches. Touches happen at least twice. Touch the x-axis. What other word that we're using a lot is as a synonym of zeros? Or synonymous? You gotta know this. Zeros are where you do what? What kind of intercept? 2. There's x's and y's. Is it an x-intercept or a y-intercept? It's an x-intercept. Talk about zeros. Zeros are x-intercepts. What they are. We call them zeros because on the x-axis, y is what? 0. Get over there, kids. It's actually one of the most important things in a math class. X can be -3, or x can be 2. There's 2 zeros. Plotted. I also asked for the y-intercept because the y-intercept is easy to get. Milo, how do you get a y-intercept? No, that's the x-coordinate of the vertex. Quadratic. Parker, how do you get a y-intercept? 0 and right. Yeah, you let x be 0. Y-axis. Anywhere on the y-axis, what's x? 0. Common sense idea. Just let x be 0. Of course, it's math. We don't use a whole lot of this kind of math every day. So the y-intercept would be at 1/6 of a 0 plus a 3 times a 0 minus a 2 all squared. Then you just crank out the numbers. I feel like a 0 plus 3 is 3. Pretty confident in that. What do you get when you square -2? 4. So what's a 6th of 3 times 4? 2. Cross the y-axis at 2. Step 4 is to think about end behavior. When you think about end behavior, what you're thinking about is the power function. Power functions determine end behavior. So let's find the power function. What's the constant going to be? 1/6. What power of x is given to you from the factor x plus 3? X. What power of x is given to you by the factor x minus 2 squared? X squared. So here's our power function. 1/6 x cubed. How does 1/6 of x cubed start its day? Low. How does it end its day? High. All right. Let's see. At -3, you guys told me we crossed the x-axis, right? Didn't you tell me that? So we're going to come in from -infinity. We're going to cross the x-axis at -3. And since we're not plotting any other points, about all you can tell me is eventually we're going to have to run into the y-axis, right? I really don't care what happens in between. I'm going to run into the y-axis. After running the y-axis, what has to happen? I have to grab that point down there. Was that a crossing or a touching? So after I run into this point, and just to satisfy end behavior, I have to immediately bounce back up, don't I? Otherwise, I don't satisfy end behavior. That's all there is to it, you know, connecting all the ideas and connecting the dots. And that's a pretty good graph. Now, we don't know exactly what happens when x is -2 or -1, but big deal. We don't have to. It's about rough graphs. Truth is, on a graph, the only thing you really need is x-intercepts and y-intercepts. The rest of it's just, who cares? It really is. There's hardly anything to be gained from the rest of it. Halfway done. Hopefully we get enough done. The rest of your notes are pretty simple. We're actually going to skip this one. And we're going to jump into the idea of turning points. A turning point is where a graph basically goes from increasing to decreasing or vice versa. It's where the slope changes. That's all it is. It's where the slope changes. And I guess I should add to that, from decreasing to increasing and vice versa. Vice versa, all right? And they're literally called turning points because it turns. I don't even know that you need that much of a definition. Anybody know how many turning points? Anybody know how many turning points this graph has? There's 4. That's a turning point. That's a turning point. That's one. That's one. There's 4 of them. That's where the graph turns. And the whole point of this slide is to establish the relationship between turning points and the degree of a polynomial. The whole point of this slide. So you guys told me this thing had 4. That's right. There are 4 of them. Based on end behavior, is it of even or odd degree? Odd. Starts high, ends low. It's actually a negative x to the odd, isn't it? Starts high, ends low. That's a negative x to the odd. Not too worried about the negative part of it. Something I should have asked in here, and I didn't, I don't know why I've never fixed it, is based on x-intercepts, what is the degree? How many touches you see? I see 2 touches. 2 touches is how many zeros? 4, that's right. At least 4 zeros. It is at least. And how many crosses you see? I see 1 cross, which is at least 1 zero. So, what's the least number of zeros it has? 5. It is at least x to the 5th. That kind of lines up with your thinking about x to the odd, doesn't it? Should, otherwise something's wrong. So based on what we've been able to determine from the graph, it's at least x to the 5th. It is negative x to the 5th. I just didn't feel like typing the negative symbol. I was more interested in the power, to be honest with you. It's got 4 turning points, 5th degree polynomial. There's a relationship right here, smack dab on this graph. To go from turning points to the degree of the polynomial, what do you do? It's 4 turning points, 5th degree polynomial. How do you turn a 4 into a 5, kids? Add 1. That's what turning point theorem is. That's what it is. So do you think the number of turns might indicate a possible degree? You should, because it does. Turning point theorem simply says that the degree, or the least degree, it is least degree, of a polynomial is the number of turning points plus 1. That's all it says. If you want the actual math definition, the actual mathematics definition is that x to the n has at most n minus 1 turning points. Which is a hard definition for some kids to understand. I mean, heck, it's got the letter n. You guys still aren't sure what a sub n is. Are you? That's turning point theorem. I'd like to at least get through the next slide. You guys get out of here, what, 12:19? 18? What is it, 12:14 now? So I'd like to get through this. A polynomial of degree 5 has blank turning points. At most. The theorem is at most. That's what I wrote, isn't it? X to the n has at most n minus 1. The theorem is at most. It might have 3. It might have 2. It has at most 4. Another similar question. Now it's degree 9. At most. Don't forget the wording at most. A lot of kids forget the wording at most. At most 8. Any questions on that? It's just take what I want, isn't it? The last question is the other way around. The graph has 12 turning points. What is its least degree? Huh? 13. The least degree is 13. We've been taking away as we talk about turning points, so now we add back. So the least degree is x to the 13th. Could it be x to the 14th? Yes, it could be. But at a minimum, it is x to the 13th, and that's turning point there. And that's enough notes, because there's no way we can do the last one. We should, though. I might put it in your notes for tomorrow. It's a nice little problem about a box.